Have you ever wondered what it would be like if something could grow without ever stopping? Not just every year or every month or even every second, but constantly in a smooth, unbroken line? Well, today we're going to dive into the math that makes that idea possible: continuous growth. Right, we're all pretty used to the idea of compound interest, where you get a little boost at set times. But in the real world, things don't really wait around. Think about it. Bacteria don't check a clock to multiply, populations expand continuously, and radioactive elements decay in this constant, uninterrupted flow. So how on earth do we model something like that? So on one hand, you've got this stuff we already know, compounding periodically, yearly, monthly, daily. The more often you do it, the better the result. But what if you could push that to the absolute limit? What if you could compound an infinite number of times? Well, that's exactly what continuous compounding is. It's the ultimate nonstop engine of growth. And here's the really cool part. You'd think that making things infinite would make the math harder, right? But it actually does the opposite. The formula gets cleaner, simpler, and way more elegant. So let's meet the new tool we'll be using for this. A equals PE to the RT. So just to put a fine point on it, continuous growth is what we call it when that compounding is happening an infinite number of times all the time. This simple formula is incredibly powerful because it turns out to be the perfect way to describe how so many things in the natural world actually work. All right, let's break this formula down piece by piece. A is easy. That's the final amount, what you end up with. P is your principal, or your starting amount. R is the annual rate, but you got to remember to write it as a decimal. T is just the time, in years. And then there's E. That's Euler's number, a super special constant that's kind of like the natural base for all growth in the universe. Now, the real magic here is all in that little letter R, the rate. If R is a positive number, you're looking at growth. Think investments or populations getting bigger. But if R is negative, now you're talking about decay, like a radioactive substance fading over time. That one little minus sign literally changes everything. Okay, enough with the theory. The absolute best way to really get a feel for this formula is to see it work. So let's get our hands dirty, plug in some numbers, and solve a couple of real-world problems. First up, an investment scenario. Let's say we have $2,000 earning 5% compounded continuously for 8 years. Step 1, identify our variables. P is 2,000, R is 0.05, and T is 8. Step 2, we just plug them into the formula. After a quick calculation, we see that our final amount is about $2,983.65. Simple as that. All right, now let's look at a decay problem. We're starting with 50 grams of a substance that decays at 3% per year. Now, because it's decaying, our rate, R, has to be negative 0.03. That's the key. We plug everything in, and we find that after 20 years, we're left with about 27.44 grams. Okay, so we keep calling continuous compounding the ultimate form of growth. But how much of a difference does it really make in the real world? Let's take $10,000 at 6% for 15 years and see what the difference is between compounding monthly and compounding continuously. And here are the results. With monthly compounding, we end up with a little over $24,500. With continuous compounding, we end up with just a little bit more. As you can see, the difference is there for sure, but maybe it's not as massive as you might have thought. In fact, the exact difference over those 15 years is just $54.94. And this actually reveals a really important idea. As you compound more and more often, going from yearly to monthly to daily to every second, those extra gains you get start to get smaller and smaller. Continuous compounding gives you the absolute maximum, but it isn't some magic trick for infinitely more money. So we've seen how powerful this formula is, but like any powerful tool, there are a couple of common spots where it's really easy to trip up. Let's go over the 2 biggest mistakes so you can avoid them. The number 1 most common mistake with decay problems is forgetting that negative sign on the rate. It's so easy to do, but if something is getting smaller, R has to be negative. If you forget it, you'll actually calculate exponential growth instead of decay, and your answer will be completely wrong. And here's the second big trap: using this formula when you're not supposed to. This formula is a specialist. It has one job: to model continuous growth. If a problem says compounding monthly, quarterly, or annually, you have to go back to the standard compound interest formula. Don't mix them up. So you might be thinking this is just for money problems, right? Well, it turns out this little formula is hiding absolutely everywhere, from the world of finance all the way to forensics.
Seriously, scientists use this formula all the time. Archaeologists use it for carbon dating to figure out how old ancient artifacts are. Forensic scientists can use a version of it to help determine a time of death. Biologists model population growth with it, and doctors use it to understand how quickly a drug leaves the human body. It's truly a fundamental part of how we understand the world.
So we've gotten really good at using the formula to find the final amount, A. But what if you flip the question? What if you know how much you started with and how much you ended with, but you want to find out how long it took to get there? How do you solve for t when it's stuck up there in the exponent? Well, to pull that t down from the exponent, you need a special kind of mathematical tool. You need the inverse of an exponential function. And that amazing tool is called a logarithm. It's the key that unlocks a whole new world of problems we can solve.